Modern aerial bombing is kind of like giving birth, and not just because both involve a lot of pushing. See, today's fighter jets fly way faster than the bombers of World War II, which creates a unique problem. Gravity alone just doesn't cut it anymore. If you simply drop a bomb at high speed and low altitude, it might not go down at all. Thanks to the airflow around the aircraft, there's a pocket of high pressure below the plane that can literally push the bomb upward. This is the reverse of what happened during World War II, when high-flying bombers sometimes accidentally dropped their payloads on friendly aircraft below. But in the jet age, bombs can zip sideways or even up, putting nearby aircraft at risk. That's why modern jets don't drop bombs, they eject them. But let's start with how it all works under the hood. Take the F-35. To release a bomb, it has to open its weapons bay doors, which sounds simple. In fact, both the F-35 and the F-22 can open their bomb bays at supersonic speeds, up to Mach 1.5 and beyond. How those doors don't get torn off mid-flight, that's pure American engineering wizardry. Also probably why Americans don't have universal healthcare. But hey, priorities. When everything works right, the bomb separation is fast, smooth, and terrifyingly effective. But getting to that point takes science. A lot of science. Before a bomb is ever paired with a real aircraft, engineers perform endless tests in wind tunnels and drop pits. They simulate airflow around the bomb bay, test bomb behavior at different speeds, and make sure the thing won't boomerang back into the aircraft. Only after all that do they move on to live test flights. The magic behind this controlled chaos is a little device called an ejection rack. It holds the bomb securely and, when the time comes, launches it away from the aircraft. Since bombs aren't self-powered like missiles, they need help leaving the aircraft's slipstream. Yes, we use explosive to deploy other explosives. Welcome to modern aviation. Back in the day, bombers couldn't open their bays at supersonic speeds, so designers had to get creative. The A-5 Vigilante, for example, ejected its nukes out the back, between the engines. The Vigilante earned the unofficial title of Nuke Pooper, a name it probably didn't ask for, but totally earned. Even today, pooping bombs isn't entirely a thing of the past. Under the Harvest Hawk program, at first, the rear of the aircraft had to be depressurized, meaning the crew had to wear oxygen masks while launching bombs. Later, upgrades added side door launch tubes and eventually a full-on bomb launching tail section, turning the C-130 into a flying bomb dispenser. A literal poop monster of destruction. But separating the bomb from the aircraft is just the beginning. Now the real challenge begins, hitting the target and, if needed, going through it. Back in World War II, bombing was anything but precise. A bomber at 20,000 feet had less than a 2% chance of hitting a 100 square foot target. That's why it took hundreds of bombers to destroy a single site. The same held true in Vietnam, where over 800 bombing runs failed to destroy the Thanh Hoa Bridge. But in 1972, 11 F-4 Phantoms armed with just 24 laser-guided bombs took it out in a single day. Just like that, smart bombs changed the game. Laser-guided bombs, or LGBs, use a targeting pod or ground laser to paint the target. The bomb's seeker homes in on the reflected laser light and adjusts its flight with tiny fins. Suddenly, bombs could hit within 20 feet of the target instead of 400. But LGBs have a weakness: bad weather. Fog, rain, or clouds can block the laser. Enter the JDAM Joint Direct Attack munition. It adds GPS and inertial guidance to standard bombs, allowing them to hit targets with 16-foot accuracy in any weather: day, night, rain, or snow. And while the regular JDAM has a 15-mile range, the extended version can glide up to 45 miles. That's rocket range with a bomb-sized punch at just $35,000 per unit. The AGM-154 glide bomb flies up to 80 miles but costs way more, upwards of $750,000. If you want to go really far, cruise missiles can reach over 1,000 miles, but they're 10 times the price and carry smaller warheads. Still, they keep pilots far from enemy air defenses, which is a major bonus. Of course, once a bomb drops, the final step is figuring out, did it actually work? That's where battle damage assessment comes in. But if your bomb happens to be nuclear, then precision becomes less important. You don't need a bullseye when the explosion covers a city block. Still, you don't want to get caught in your own blast. That's why toss bombing was invented. Bombs are lobbed upward so the aircraft can turn and run before the blast hits. That's where small diameter bombs, SDBS, come in. Each one weighs just 250 pounds, meaning a fighter can carry 4 of them instead of one big 2,000-pounder. That means more targets destroyed, less collateral damage. The GBU-39 has a 69-mile range and hits within 3 feet. The newer GBU-53 Stormbreaker can even hit moving targets in all weather thanks to its advanced seeker. When the bomb reaches the target, that makes them perfect for bunkers or for catching curious enemies returning to assess the damage. To smash deep underground bunkers, you need bunker busters. These are long, narrow bombs made from insanely strong steel like like Eglin steel, which can survive over 190,000 pounds per square inch. The bomb's narrow shape helps it punch through layers like a nail driving into wood, and its delayed fuse ensures it explodes only after reaching the right depth. Take the GBU-57, the massive ordnance penetrator. It weighs over 13 tons and can tear through 200 feet of concrete, rated at 5,000 psi. But if you just double the concrete strength, you only need a quarter of that thickness to resist the bomb.